When you perform an analysis, the analysis settings screen will be displayed. Select the analysis type that you wish to perform. A standard analysis indicates one where we are assuming the stack is installed in the vertical position, and an analysis will be performed to evaluate the dead load and lateral loads acting on the system. The lateral loads would be wind, seismic, etc. The stack is modeled as a series of beams. We start with a long beam that goes from the top of the stack to the bottom of the stack. Anywhere that we specified something is happening on the stack, we insert a node and divide the beam. This could be the addition of a platform, change in diameter, or any other attachment we may have specified. Now we don't want our beam elements to be too long because that can negatively affect our results. We can control this with the minimum element size setting on this screen. Typically, this is about 10 feet or 3 meters. The application will now go check every beam in our model, and if any are longer than this specified value, then it will further divide to ensure that we don't exceed this amount. Although a smaller number will result in a more accurate analysis, it also causes the analysis to take longer and the output report to be longer since there are more points that are analyzed. Next, we have the installation temperature, which represents the ambient temperature that is expected when the stack is going to be installed. If the stack you are analyzing does not have guy wires, then the only purpose of this value is to use it as the reference ambient temperature when calculating the vertical deflection due to thermal expansion. Without guy wires, there is nothing resisting the stack when it tries to expand thermally, and so we only calculate the thermal expansion for the user's reference. It's not used in any other part of the calculations. If we do have guy wires present, then this entry becomes much more important. When the stack tries to thermally expand, that growth is restrained by the guy wires. It can represent a very large force on the guy wires, stack, and foundation. The temperature entered here represents the most likely ambient temperature that would occur when the maximum lateral load condition were to occur. For example, if you were designing this stack for a hurricane region, then hurricane wind loads are the most likely controlling lateral load. We wouldn't expect those to occur with a temperature near freezing. A value of 70 degrees Fahrenheit or 21 degrees Celsius is more likely. Next, we select the analysis method. For a typical self-supported stack, a linear analysis is perfectly fine. If you have concerns of p-delta, then you can select the nonlinear analysis. P-delta refers to the secondary moment that arises in a structure due to axial loads acting on a laterally displaced member, amplifying deflections and increasing instability under load. P-delta is typically a concern when a stack becomes very slender and has high lateral displacements. If you are within the deflection limits recommended by Meca, then typically P-delta is not a concern. If you have a guy wire supported stack, then you must perform a nonlinear analysis. This is due to the nonlinear nature of guy wires, and so we need to use the nonlinear analysis to accurately account for the nonlinearity of the guy wires. When you select nonlinear, you will be asked to specify the number of load steps. The loads on the stack are calculated, and when a linear analysis is performed, that full load is applied to the structure and the resulting stresses and deflections are calculated. When we perform a nonlinear analysis, we divide up that load and apply it in increments. If the load steps are specified as 10, then that means we apply 1/10 of the load. We do this 10 times, each time applying an additional 1/10 of the full load. After each time we apply the load, the deflection and stress are calculated and added to the previous iteration. This is the way the nonlinear behavior is approximated. Entering a larger number will result in a more accurate model, but it also takes significantly longer time to perform the analysis. A value of 10 represents good accuracy for almost all situations, and there are many cases where 3 might give good results. One strategy is to use 3 while you are building and debugging your model because the computation time is much faster. Then when you think you have your model refined, you can change it to 10 and see if the results are still acceptable. On the right side of the analysis settings is a section called Issues. This will summarize any potential issues that exist on your model. It is a compilation of all validation warnings and errors that may have existed on all of the individual screens for your model. A warning is yellow in color and is just indicating that there may be a problem, and you can choose to ignore if you disagree with the warning. An error is red in color and typically means that there is a problem that should be addressed. Often you can double-click the actual message and it will take you to the area that is directly causing the problem. However, that won't work in all instances. Once we have specified the parameters, we are ready to perform the analysis. We review the results, and if the results are unacceptable, then we make the necessary modifications and then repeat the process until we obtain acceptable results.